So hello everyone, and this is basically Devabrata here. So welcome to all of you to our channel Schrödinger's cat. So in the today's class, we'll cover the quantum mechanics from the BSc and MSc students like the aspirants IIT JAM, JEST, TIFR, CSIR NET, GATE and SET. So we have the chapters like tools and postulates of quantum mechanics. Number 1, postulates of quantum mechanics. Application of quantum mechanics in Cartesian coordinate. 2-dimensional and 3-dimension system. Application of quantum mechanics in spherical symmetry. Number 6, the hydrogen atom, scattering, perturbation theory, variational principle, WKB approximation, identical particle, and the last one, number 12, relativistic quantum mechanics. So in the today's class, we will cover number 1, the tools and postulates of quantum mechanics. Number 1, today we'll discuss the linear vector space, scalar product, Hilbert space, linear independent vector space, square integrable function, Dirac notation, operators, commutators, postulates of quantum mechanics, Fourier transform and change in basis. Okay. So I just clarify one thing that for the exam point of view, today we'll discuss the chapter summary in a nutshell and the previous year questions like IIT JAM, JEST, TIFR, NET, GATE and SET. So let's get started. And the total number of questions are coming in the entrance like the JAM in this topic, perhaps 1. Okay. And JEST should be 1 and TIFR 1 or 2, CSIR NET 1, GATE 1 and SET 1 or 2 questions from these chapters, the tools and postulates of quantum mechanics. So first of all, that the chapter summary, basically some concepts and fundamental formulas for exam point of view. Number 1, that just a minute. So formally, that the scalar product of two functions, that the scalar product of two functions, that phi x and psi x are respectively is given that the psi phi, this is equal to integration psi star x complex conjugate phi x dx, where the phi xyz and psi xyz are given by basically in the 3D, that this is nothing but integration psi star phi dx dy dz in 3 dimension. So next, linear independent vector space. That suppose linear independent vector space. Suppose this is defined at the summation I1 to n ai phi I, this is equal to 0. That means the coefficient a1 a2 equal to dot dot, that is 0. Otherwise phi 1 phi 2 dot 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 phi n said to be linearly dependent. This is equal to 0 condition, and for linearly, for not equal to 0, otherwise means the not equal to 0, this is called the linearly dependent. Next, number 3. Number 3 is basically the orthonormal basis. Orthonormal basis, that is the phi I phi j. This is written as delta ij. This is basically the Kronecker delta used in tensor mathematics. So the delta is equal to 0 for not Dirac delta function, I not equal to j, and 1 for I equal to j. Next, the square integrable function. Square integrable function, that is the psi. This is nothing but integration minus infinity to infinity psi star psi dx. This is equal to mod psi square dx. Then psi x is said to be the square integrable. This is very important for foundation in quantum mechanics. Next one, the Dirac notation, number 5. Dirac notation, that means psi can be written in ket psi, and psi star complex conjugate, this is the bra psi, and the phi psi, this is nothing but phi psi. This is called the inner product, and this is written in the form integral phi star RT psi of RT d3r. This is basically the volume integral dv dx dy dz. And the properties of kets and bra and bracket, the properties of the properties of bracket notation, that is ket psi conjugate, this is the bra psi. A acting on psi conjugate, this is A star bra psi. Bra A psi, this is A star bra psi, and the phi psi whole conjugate, this is interchange of psi and phi. Okay. And the another one most important is that suppose psi is normalized, that means inner product of psi and psi, that is 1. And one more important relation is that A1 phi 1 plus A2 phi 2 B1 psi 1 plus B2 psi 2. This inner product should be equal to A1 star B1 phi 1 psi 1 plus A1 star B2 phi 1 psi 2 plus A2 star B1. This is the phi2 psi1. And the last element A2 star B2 phi2 psi2. Okay, this is the fundamental properties. Next, number 7, that is the squash inequality. It states that in mathematics that the modulus of psi phi inner product mod square, this is less than equal to psi psi with phi and phi inner product, which is analogically derived from, this is derived from, that is the A dot B less than equal to mod A square into mod B square. Simple mathematics. Next, triangular inequality. This is some inequalities in quantum mechanics. Triangular inequalities, that is the square root of psi phi and psi plus phi. This is equal to square root of inner product of psi psi plus phi and phi. Next, the orthogonal state. Orthogonal state is basically for the psi phi inner product should be 0. Okay. Next, orthonormal state. This is orthogonal, and another one, the orthonormal. Orthonormal state, this basically that inner product psi with phi, this is equal to 0. Psi with psi is 1, and obviously phi with phi is always 1. This is the orthonormal state. Next, go ahead. Suppose if another important properties, psi and phi belong, however, to different vector space, then the state phi with psi, this is called the tensor product. Okay, tensor product of psi and phi state. Next, some operators. Number 9, very important. The operators. First one, the identity operator. That is, I acting on psi is nothing but ket psi. This is identity operator. Next, parity operator. Pi acting on psi r. This will become psi of minus r. For negative parity. Okay. Basically the odd parity. And for even parity, it should be the positive. Next one, the gradient operator. Grad psi r. This is called the gradient operator. Next, this is linear momentum operator. P acting on psi is equal to minus IH cross gradient of psi r. Okay, this is the linear momentum operator. Linear momentum, this is the gradient, this is parity, this is identity. Next, linear operator. Basically, A lambda 1 psi 1 plus lambda 2 psi 2. This will become lambda 1 A acting on psi 1 plus lambda 2 A acting on psi 2. Product of two linear operator A and B written AB defined as AB acting on psi. This would become A B acting on psi. This is the definition of linear operator. Next is very important, the matrix representation. The matrix representation. Number 10. So, okay, we just do in the next page. The matrix representation of the operators. Okay. That is, suppose psi can be written in the form the linear combination of Ci phi I. Ci be the complex number, where the Ci, that is the inner product of phi I and psi. Okay. And the ket psi, the state is the orthonormal basis of psi I. That is, that basically the ket psi, this is nothing but the column vector. Suppose phi 1 psi, phi 2 psi dot dot. This is written in the form C1 C2 dot dot, is nothing but the column vector. Next, this is the ket state. Next, the bra state. This is that the row vector, basically the row matrix, that is the conjugate of phi 1 psi inner product conjugate. Next element, phi 2 psi conjugate. Okay, dot dot. This is nothing but row matrix of C1 star C2 star dot dot. Basically the row matrix. This is the column matrix. Okay. And the transpose of the operator A, transpose of the operator, basically the Aij transpose, this is equal to phi j A phi I. This is the mathematical form of the transpose operator. Next, the eigenvalue and eigenvector. Number 11. Eigenvalue and vectors. You already familiar with in your mathematics matrix. Okay, nothing but the linear algebra. So if an operator is defined such that A acting on psi is equal to lambda psi, then the lambda is said to be the eigenvalue. And the ket psi, this one, the ket psi, this is called the eigenvector corresponding to the operator corresponding to lambda I of an operator. Okay, this is the definition of the eigenvalue and the eigenvector. So now the correspondence between the ket and bra. Suppose this is number 12. A acting on phi. This is equal to suppose psi. Then the dagger means the conjugate. This will be the bra psi. Where A dagger, this is nothing but the Hermitian adjoint. Hermitian adjoint is basically A dagger is equal to A dash transpose. Okay, this is written as in this form. This one, Hermitian adjoint. Next, very important, the Hermitian operator, number 13. Hermitian operator, the operator is said to be Hermitian, that is the A dagger is equal to A. Simple, in matrix. This is the definition. And mathematically, it is written the phi I A phi j is equal to phi j A phi I conjugate. Okay. Next is very important, the commutator. Commutator. That the commutator of AB is nothing but the AB minus BA. And if the commutator of AB is equal to 0, then it is said that A and B, very important, operator commute to each other. And the physical interpretation is that the AB simultaneously measurable. Okay. Next one, some properties. And one is important is that the projection operator. Projection operator, this is the P dagger equal to P with P square equal to P. This is the projection operator. Next, some important properties of commutator. Properties of commutators. First one, antisymmetric. AB commutator is equal to minus of BA. Okay. Anti-symmetric. Next, A plus A with B plus C plus D. This is equal to A plus B plus A plus C plus A plus D. This is the linearity. Next, AB commutator with C. This is order is very important. AB C plus B with AC. Order is very important. This is the distributivity. Distributivity. And the last one, Jacobi identity. You all are familiar with in your classical mechanics Poisson bracket. That is A with BC whole commutator plus B with CA plus C with AB. Total is equal to 0. This is called Jacobi identity. Very important. Okay. So these were our the part 1. Next, go ahead in our part 2. Part 2 is very important for exam point of view. That is the postulates of quantum mechanics. Part 1, we are the tools. Next, it is our postulates of quantum mechanics. Number 1, physical measurement of a state A acting on phi n is equal to an phi n. This is basically the probability. Probability is the physical measurement defined as P of an is nothing but mod of phi n inner product with psi square, divide the normalization psi with psi. This is the probability for the non-degenerate case. Okay, non-degenerate case. Next, if the degree of degeneracy, if degeneracy means suppose the energy level E is split into 3 parts, E1, E2, E3. This is the degeneracy. Ci equal to 3. If the degeneracy is Gn, then the probability would become P of n equal to simple summation of I1 to Gn. Gn is here the degeneracy. Mod of phi n I psi with normalization psi with psi. Okay. Next, state just after measurement. This is called the projection. Very important. Projection of a state psi. This is nothing but Pn multiply with psi state divided by square root of psi probability and psi. This is called as the expectation or average value. In quantum mechanics, this is called as the expectation value. Number 3, time evolution state. Time evolution state, that is IH cross ddt of psi t. This is equal to ht acting on psi. This is the time evolution. Number 4, the psi defined for a wave function for satisfying a wave function. First, the single valued and finite. Number 2, continuous. Continuous means left hand limit and the right hand limit should be same. Differentiability means the left hand derivative and the right hand derivative should be same. This is called the differentiable. Next, square integrable. We already defined. Square integrable. This is the condition of a psi for satisfying a wave function. Next, the expectation value. Expectation value means the psi A should be the operator over psi normalization. This is written in the form that summation over n an phi n psi mod square divided by the normalization psi. Because psi n a psi n psi m a psi n, this is nothing but the an delta mn. So therefore a should become summation over an p of n. This is the probability. Okay, this is for the discrete. And for the continuous system, the summation changed to be the integral. Okay, the continuous system, this is very important. A should be equal to integral minus infinity to infinity a psi a square mod psi a square. This is nothing but the probability dA divide the normalization over mod psi a square dA. This is very important for continuous system, the probability, the expectation value. Next, number 6, the momentum and position representation of a wave function. Momentum and position representation. Momentum and position representation. Okay. Suppose x acting on r, this is equal to xr. Px, x component of linear momentum acting on p, pxp. In such a case, r x psi, this is the x r psi, and the r psi inner product would be the psi r. Okay, so we should write the phi x psi, this is nothing but the integral for 3 dimension D3R, inner product of phi and R with R x psi. This is written in the form integral D3R, the phi star R x psi R. Okay, this is in the position space. And in the momentum space, it should become px psi. This is equal to px p psi. And the p with psi inner product should be psi p. Simple. So now the phi px psi, this is equal to d3p phi p, as usual, p px psi. This will become the integral d3p phi star p px psi p. This is the momentum representation. Okay. Next, Fourier transformation and change in basis. Fourier transformation and change in basis. So, change in basis from one representation to another representation. Suppose ket p 1 by square root of twice pi h cross exponential I px by h cross, and it should become the AP is equal to 1 by square root of twice pi h cross integral minus infinity to infinity psi x e to the minus I px by h cross, and in the 3 dimension it should become 1 by twice pi h cross to the power 3 by 2 integral minus infinity to infinity psi x should be psi r e to the minus I. It should be p dot r by h cross, and it should be dx here. Dx should be changed into the d3r volume element, and the AP is nothing but the expansion coefficient of the momentum state ket p. Next, the delta Dirac. This is the Dirac delta. Okay, first one should be the Kronecker delta. It should be the delta Dirac. That is the orthonormalization relation. Very important. Orthonormalization relation, that is the R dash inner product delta of R minus R dash. This is the P prime is delta P minus P dash. This is the orthonormalization relation. And next one is very important, the closure property or closure relation. Closure property or closure relation, that is the integral D3R ket R bra is equal to identity. This is in the position space and it should be right in the momentum space, that is the D3P ket P bra P is equal to identity matrix. And once the two properties, orthonormalization relation and the co-closure property, satisfy simultaneously, it should be called the completeness relation. Okay. Completeness. Once two property satisfy. Next, the parity operator. Simple. Pi acting on R is equal to minus R. This is written in the form R pi psi is equal to psi of minus R. Suppose psi of minus R equal to psi R. This is called the even parity. And the eigenvalue plus 1 or minus 1. Parity eigenvalue. And when it should become minus of psi R, it should be called the odd parity. Okay. Next one. Number 10. Any function fx can be expressed in terms of psi x. That is, the function of x equal to summation n1 to infinity cn psi nx, where the psi nx equal to integral psi n star x fx dx. That is the main theory, is the funda, that the any function fx can be written in terms of psi nx as an wave function. Okay. So let us conclude our chapter summary class for the chapter the tools and the postulates of quantum mechanics, basic introductory class. Next we go ahead in our problem discussion session. Problem number 1. Is coming from the IIT JAM. The wave function for quantum mechanical particle is given by psi x equal to 3 by 5 phi 1x plus 4 by 5 phi 2x, where phi 1x and phi 2x are eigenfunction with corresponding energy eigenvalue minus 1 and minus 2 electron volt respectively. The energy of the particle in the state psi is equal to what? Simple. That is equal to, by the definition of expectation value, divided by psi x. Put this value minus 1 electron volt into 3 by 5. Probability means the P mod Ci square. Okay. So 9 by 25 plus minus 2 into 16 by 25. It should be equal to minus 41 by 25 electron volt. Option A is correct. Okay. Next. Problem number 2. Get the state of a system is given by get psi equal to get phi 1 plus 2 phi 1 2 phi 2 plus 3 phi 3, where phi 1, phi 2 and phi 3 form an orthonormal set. The probability of finding the system in the state phi 2 is what? This is basically the NET type question. So probability of state phi 2, simple. Phi 2 means coefficient 2 square by the normalization, total. This is basically the probability of phi 2 means this one, probability of phi 2 by the total probability. This is the 1 square plus 2 square plus 3 square. This should be equal to 2 by 7 or 0.28. 0.28, okay. This is the net 0.28, you should be right. Next, the number 3 question from JEST. The wave function of a free particle in one dimension is given by psi x equal to a sin x plus b sin 3x. Then psi x is the eigenstate of what? Simple. We know one thing, that psi of minus x is equal to psi x when this is even, minus of psi x for odd. So psi of minus x equal to a sin minus x plus b sin minus 3x. This is equal to minus of a sin x plus b sin 3x. So psi of minus x equal to minus of psi x. That means the negative parity. Negative parity means it should be the parity operator. Simple. Option D is correct, parity operator. Number 4. CSIR NET. Consider, I just beg your question. Okay. Consider the operator x is equal to Ly Pz minus Lz Py, where the Li, Pi denote respectively the components of the angular momentum and the momentum operator, the commutator x with x, where x is the x component of the position operator, should be what? So x is given Ly Pz minus Lz Py. We know the y component of orbital angular momentum r cross p. This is the z px minus x pz, and the Lz should be x py minus y px. This is given. So you have to find ax with x. Just put this value, that Ly Pz with x minus Lz Py with x. Simple. It should be Ly x Pz. Distributivity product. Distributivity. Basically the distributive property. Lzx Py. Order should be maintained like the chain rule of differentiation. This should be Zpx with x Pz plus ypx with x Py. Z should be going outside with the bracket px x Pz plus y pxx with py. Put this value minus ih cross z pz plus minus ih cross y py. It should be equal to minus ih cross should be common here, z pz plus y py. So I think option A should be the correct. Next, go ahead. Our last problem coming in the TIFR 2017. Denote the commutator of two matrices A and B by AB equal to AB minus B. The anti-commutator AB with curly bracket equal to AB plus B. If the anti-commutator is equal to 0, we can write A with BC commutator is 1. That is A with BC commutator. Simple. This is the ABC minus BCA. This would become minus of BAC minus of BCA, because anti-commutator of AB is equal to 0. That means AB plus BA equal to 0. That is the AB equal to minus B. We should put here. So minus B should be common here. That is the AC plus CA. It should be minus B anti-commutator of AC. Minus B anti-commutator of AC. Option C is correct. Okay. So we now complete here our theory as well as the problem discussion session. Now, for your better practice, conceptual and understanding, these 5 are your homework. Just pause this video and take a screenshot quickly. And after solving this homework, you should contact me, solve this homework, and if anyone needs this file, like the study material of my YouTube lecture, just mail without no hesitation with this ID, catschrodingers1935@gmail.com. So I think this video will be helpful for the aspirants of the IIT JAM, JEST, TIFR, CSIR NET, GATE and SET. For both the BSc and MSc Physics student aspirants. And we have the another lecture session for the 11-12, both for physics and mathematics, NEET, UG and JEE main and advanced. So last but not the least, thank you very much. Stay well and happy. Have a nice day.